Greetings. The property energy presents us with two ambiguities. First is that its reference point is arbitrary, and therefore any object could have lots of energy or none, or even negative energy, and all are correct. Second is that it's not clear how much of that energy could produce work. The property availability just solves these two problems. Availability sets the reference point as the ambient and then gives us the maximum possible work if the material comes to rest with that ambient. This work is in fact impossible since it only happens if all those fictitious processes towards coming to rest are reversible. Availability does not present us with a new law, but at the same time, a combination of the first and second laws gives us an equation for the change of the property availability through a process. I use one of my recent exam problems just to start with our discussion about availability. The problem is about a cylinder piston arrangement. So we have a cylinder and there is a piston and there are stops where the piston could not move below these stops. So there is a minimum for the volume inside the cylinder. Now, inside the cylinder is water, there is some liquid, and there is some vapor. They are both in the cylinder, and the problem tells us that the mass of the water is 0.15 kilograms, and it's a mixture of vapor and liquid. Its temperature, T, is 350 kelvins, and they are in equilibrium. Now, the volume V1 is, let's call it T1 and M1, and V1 is 0.13285 cubic meters. That's the initial volume. Now, to lift the piston, we need a pressure of 1500 kilopascals. So, required pressure to lift the piston is 1500 kilopascals. Now, the problem tells us with one addition, which is to try to give us a point. There is a plate over this. There is a plate over this liquid at its initial condition. So there is a plate. This is a plate. The plate has no mass, so m of p equals 0. It moves freely, which means p at its both sides are equal, which means p is equal on both sides, and also it conducts heat freely. So conducts heat freely. Therefore, T is equal on both sides. The only thing that cannot go through this plate is mass. The rest of the things are good. The rest of things can move. It's only mass that does not go through this plate. Now, um, um, now uh, we start heating this cylinder. So we add Q to the problem. And the question is, first, when would all liquid turn to vapor? When would all liquid turn to vapor? And two, when would the piston start to lift? At what temperature? At which temperature? Would the piston start to lift? Of course, the other thing that we want in this problem is that you uh, draw the diagram, also simplify the conservation equations, find the properties, and then combine them all to find the final solution. Well, a first step to solve this problem is to refer to the diagrams or properties and see uh, where our problem is, what the properties are. So we go to the tables and look for saturation properties for 350 kelvin. What we learned for it is that at these properties, at this temperature, the saturation pressure Psat equals 0.041683 megapascals, which is equivalent of 41.6 kilopascals, and this is far less than the 1500 kilopascals, which is required for lifting the piston. So we're in a good, we know that this piston would rest, at least in the initial condition. Now, the other properties are Vf, which is 0.0010 to 70, and Vg is 3.8419. Both are cubic meters per kilograms. Uf is 321.75 kilojoules per kilograms, and Ug is 2477.6 kilojoules per kilograms. Hf is 321.79 kilojoules per kilograms, and Hg is 2637.263 7.7 kilojoules per kilogram, and SF is 1.0380 kilojoules per kilograms Kelvin, and Sg is 7.6549 kilojoules per kilograms Kelvin. These are the properties of water, regardless of where our problem is. It's a good practice to draw our diagram right away and just present these properties on a diagram. It helps us. This is T, which is in kelvins, and this is V, which is in cubic meters per kilograms. Please note that the book, different books have different tables, and they are all correct. That's not the point. But their different tables gives us different values. I mean, the book by Terence has temperatures in Kelvin. The book by Sengel or Zontag have temperatures in degrees centigrade. So they are arranged for those temperatures. Also, the book by Moran has temperatures between 0 and 5. I mean, most books arrange their temperatures for, say, 5, 10, 15, 20. But this book arranges its temperatures for 2, 7, 12, and the rest. And so, before you go for an interpolation, just have a look at different tables and learn which tables different books present, and then you could easily find your properties from the book and from the table that requires minimum interpolation and gives you just the values, and that is the best case. So the saturation line is this one, and this is the critical point. This value is 22.064 kilopascals is the pressure, and 393 degrees C is the temperature. But that's what we know about this point. Now, let's draw the line here. This is the saturation line for 350 kelvins. The pressure on it, this is the constant pressure for it, which is 41.7 kilopascals, and the values that we have just read from the tables gives us these two values, which this one is 0. This is 0.0010 to 70, and this value is 3.8419. So we have these two values. Now, just to find out where our problem is, what we should do is to calculate. We have the mass, we have the volume, and so we could just divide them and find where our initial point is. V1 equals the volume, which is 0.132825 divided by mass, which is 0.15, and the outcome is 0.8855 cubic meters per kilogram. So and this value is somewhere between this point and this point. So we have say point 1, and we know that its value, its specific volume is 0.8855. This is the specific volume of the point here, and that is our initial point. Its pressure is 41.7, and its temperature is 350, and the specific volume is 0.8855. You see, the method I used for this is very important that you should use it as well. You see, I first determined where what our steam properties are. So I knew the specific volume for saturated liquid, then I knew the specific volume for saturated vapor, and then so these are these values regardless of what our problem is. These are steam properties, water properties, and steam properties. And then I decided where our problem is. I calculated the specific volume for our problem and then positioned our initial point on this diagram. So, in fact, what I have done, I have distinguished between our problem and water properties. It is very good if I just draw our problem in green. It means that if I just draw this in green, okay, this would be our problem, and the blue ones would be steam properties, which are different. Okay, so we have to distinguish between water properties and our problem. Once we have calculated the specific volume for our initial condition, then we could also calculate other properties. And the key property we have to look for is quality, because that will lead us to other properties. Now, to calculate quality, we could write x equals 0.8855 minus 0.0010270 and divided by 3.8419 minus 0.0010270, and the outcome would be 0.23, which is the quality of water inside this cylinder at its initial condition. Well, now with the knowledge of quality and also the knowledge of internal energy, enthalpy, and entropy, we could calculate all these values for our initial condition. So just to start with, U1 would equal UF plus X times UG minus UF. And to put numbers to it, this would equal 321.75 plus 0.23 times 2477.6 minus 321.75. And the outcome for U1 would be U1 is and the units is kilojoules per kilograms. We have to write down the units as well. With the same practice, we could also calculate H1, which would result in 854.5 kilojoules per kilograms, and then S1, which is 2.56 kilojoules per kilograms. So what we know now is that we have all the possible knowledge for our initial condition, and that is clear and straight. So our next step is to write down the thermodynamic laws and simplify them for the problem at hand. But to write these equations, we have to first decide on our control volume. Our system, our boundary, would be all that there is inside this, all that there is inside this um, cylinder. These are our equations, and you see, this is the mass conservation equation, and this is the energy equation. The second law of thermodynamics and the availability equation. I would just describe each of them in this problem first and then simplify them, and then you would see the meaning and the meaning for the problem that we are trying to solve. So the mass conservation equation would read as dmCV by dt equals m dot I minus m dot E. And since no mass enters or leaves this boundary that I have drawn, therefore we would integrate it between initial and final condition, and therefore m2 minus m1 equals 0. Now, there is a way to modify this for our problem. Instead of m2, we write v2 over v2, and instead of m1, we write v1 over v1, and that equals 0. We know that v2 equals v1. We don't know it, but for the time being, since the pressure is smaller than the pressure that would lift the piston, at least we have two alternatives. First is that the volume remains constant and the pressure increases. It could happen that first we would have saturated vapor without the piston being lifted, or we would have piston being lifted. We don't know yet just which one would happen after increasing the temperature. So what we would do, at least we know initially that the piston does not move. So what we do is that we keep V2 equals V1, and therefore we conclude that V2 equals V1. So our initial condition, where we start with, is that the specific volume would remain constant. So in this problem, what we have initially is that the specific volume remains constant, and therefore we go up here. Now, there are two questions. Is the pressure here 1500 kilopascals, or is it less? If it is less than 1500 kilopascals, we conclude that we first reach the saturated vapor for all that there is inside, and otherwise the piston would first be lifted. If 1500 kilopascals is somewhere here, then the piston would start to lift. But if the 1500 kilopascals is somewhere here, then the piston would not lift, and this case of V equals constant would continue until we reach saturated vapor. But as it is for our case, for the time being, V2 equals V1, and that equals 0.8855 cubic meters per kilograms. So what we should do is that for this value, we should look inside the tables and see what the pressure is. And that's what we just do now. What we learn from the tables is that at 200 kilopascals, say this is 200 kilopascals, and at the temperature of 393.36 kelvins, the specific volume for saturated vapor is a value very close to this. Is a very good approximation for this. So the conclusion that we make is that as we heat this cylinder, the temperature goes up, the pressure goes up, the process is specific volume constant, okay, specific volume remains constant, and therefore the first point that we reach is the saturated vapor at 200 kilopascals and 393.36. So where we are is that the piston won't lift. Before any movement of the piston, we reach at the second point, and that is where all the liquid inside this cylinder has vaporized. So we now have this point here, which we can now see all its properties and all its values. And we shall calculate the rest of the properties in our next video. Cheers!